Again, welcome to Shomo Ganguly. Shomo, as many of you know already, you have been attending for this session for some time. He is talking on about Cheng's conjecture, a problem that he has worked on in 2 dimensions, and he's doing this for the last 2 sessions. This will be the third session on this particular topic, and we decided that this will be a 3-part lecture series or a mini course, but after discussing with Shomo, we figured out that it is better if we extend this by either 1 or 2 lectures more, depending on Shomo's availability and so on. So I will leave that to Shomo, but Shomo, on to you. You can just
Okay,
take it
great.
over and share the screen and everything. Yeah.
Yeah, thanks, Ashwinita. So the idea is that maybe because I have to cover a lot of prerequisites, so in that case, I think it's better to extend it by one more lecture at least. We will see that by the end of today or maybe next week. Definitely, it will be extended by one lecture. So let's see that. Maybe
Sure.
we can have one lecture more, and then in the next lecture we can just have a question answer session. I don't know, but
Absolutely.
anyways, so let's just start sharing my screen. Ashwinita, please give me a confirmation when you see my screen.
Sure. I'll do that. Yeah, something is coming up. Yes, I can see your screen.
Okay. So previously, so let's talk about the point where we left off. So previously we talked about volume forms. Volume forms are basically, if you have an n-dimensional real manifold, then it's an n form, which is, you can think of it as a n number of conforms joined together. So if you integrate the volume form on the manifold, you basically get the volume of the manifold. So now, however, so we know now we know in terms of like differential geometry how to calculate volume of something. So now the question is, how do you, so this is a way to calculate volume, but how do you calculate lengths or lengths of curves? So for that, we need this concept of Riemannian metric. So first of all, again, we talked about it last time a bit, but Riemannian metric, we will talk about it more this time, and probably we will all understand why this concept is there. So it is like an inner product. Riemannian metric on a manifold M is like an inner product on the tangent spaces. Now, you might all think that this is becoming really too difficult, but it is not. We will explain by examples how this inner product will help us to give us lengths. But before that, let's just try to give the definition. Again, the definition will also be given intuitively. So suppose you have a manifold M, and at every point you have a tangent space. So you have a tangent space here. It's a 2-dimensional real manifold. So the tangent space looks like R2. If you call this point P, then this is TPM. Now you have different tangent vectors here. Suppose you have one vector here and one vector here, V1 and V2. So now you are defining an inner product with respect to this Riemannian metric. So you write this as GP of V1 and V2. This is nothing but the inner product of V1 and V2. And this P is only denoting us that everything is happening in the tangent space of P. Now, we also need, because we are on a manifold, everything is really locally defined. Locally, they look like Rn. They are, they are globally defined, but they are essentially defined in terms of their local characteristics. So we can think of everything defined locally, and also things, when we are talking about differentiable manifolds, we want any function on them to be differentiable. That's our primary goal in differential geometry. So the idea is that this metric should be a differentiable function of 2 variables, as you can see. On the tangent spaces, we will try to make them a little bit more rigorous later. For now, you should just think of it is an inner product on the tangent spaces, And as you move through the tangent spaces, the inner product kind of changes continuously. These things are not very rigorous, but pictorially, I think they might help you. So for example of Riemannian metric, one big example that you know is the Euclidean metric. This is something which I hope everybody knows. I am just going to write them in a different way, but we are writing the same thing. Suppose we have, so Euclidean metric means on Rn. So our manifold is now Rn. And there on any tangent space, so Tp of M is just like an Rn, right? So Tp of M, which means the tangent space at any point on Rn, it's just nothing but Rn. For example, if you look at this piece of the whiteboard here, this is a piece of R2, and if you take any point P, then the tangent space at that point is also like R2. So in that case, TPM is equal to Rn, and there, so any vector v1 in the tangent space will look like summation ai del xi. Now you might I from 1 to n. Now you might think, okay, what is this way of writing a vector? Well, this is nothing. This is again just writing tangent vectors in differential forms, in a differential form. Okay, I shouldn't say the word differential form, but because it has a different meaning, it's writing the tangent vectors as derivatives. We talked about it before, because you can think of this del xi as the ith basis vector, which means it is 0, 0. In ith coordinate, you have 1 and then 0, 0. So this is the ith coordinate. Now, again, suppose you have this other basis vector, I from 1 to n, bi del xi. So now you have these two vectors in the tangent space of at P for this manifold M, which is Rn. Then we can define an inner product as just summation I from 1 to n ai bi. Well, but this is nothing but the dot product. If you think about it, if you have ai ei, pi ei, and you take the inner product, this is just like the vector dot product that we know. So this is also an inner product on this manifold Rn. For every point, you can define it in the same way. So this defines the Euclidean metric. It's also a Riemannian metric. So with this metric, Rn becomes a Riemannian manifold. Any manifold which has a Riemannian metric is called a Riemannian manifold. Now, there is this big, very deep theorem, which I'm not going to prove. It's actually not, the proof is not that difficult, but every smooth manifold admits a Riemannian metric. So basically, any smooth manifold, which means any manifold where you have smooth coordinate charts, they admit a Riemannian metric. Now we will come to the notion of length of curves on manifolds.
Sorry, Shoma, what is the meaning of admits here?
You can define a Riemannian metric. By admits, I mean you can define a Riemannian metric. So basically, the idea is simple. The idea is, if you have a smooth manifold, then locally it looks like Rn, right? So now on every Rn, you have this Euclidean metric. What you do, you basically do a partition of unity where you define, you take this manifold and you cover it with a chart, and you take a partition of unity with respect to that chart, and then on each of this chart you take a pullback of the Riemannian of the Euclidean metric, and you patch them together using the partition of unity. That's it. Anyways, if you don't understand, I mean, for the other viewer, or Sunida understands this, but for the other viewers, if you don't understand what partition of unity means, doesn't matter right now. The point is that this Riemannian metric that you give on the smooth manifold is essentially the Euclidean metric that you see, because again, a smooth manifold locally looks like a Euclidean space. So you can give Euclidean metric to all those local charts and then patch them together in some way. So length of a curve.
So sorry, I'm actually interrupting. I'll just because there are many school students here as well. So I want to clarify this for them and myself as well. I would also say this, that when you say admits, you mean that right now you'll be defining something called length of a curve, right? And then
Mm-hmm.
you'll probably define the distance between 2 points as the
Mm-hmm.
minimal length of a curve
Mm-hmm.
connecting those 2 points, and
Mm.
that distance will match the original distance function defined on the manifold. Does that uh, does that
What do you mean by
mean?
original distance function?
So is there a distance function on the manifold already? Is it a metric space already?
No,
It's not a metric space. Okay.
no. You will make
So
it a metric space once you have a Riemannian metric.
okay, okay. So what? Okay, so I think my question is this: that given a particular point on the manifold,
Mm-hmm.
we can definitely take the TPM, and
Mm-hmm.
then it's just Rn, right? It's just Rn.
Yeah.
Then we can define the inner product in that particular Rn.
Mm-hmm.
So if we do that at every point, we would have defined an inner product.
Yeah, but the problem is that for it to be a matrix, the inner product should vary continuously across different tangent spaces. So
Ah,
metric is also a function. For differentiable manifolds, we need that function to be differentiable. If you
I-
arbitrarily define inner products on each of the Rn tangent spaces, it will be a
ah,
function, but it may not be differentiable.
now I understand. So basically, what you are saying, that there is a special choice in
Yes,
each TPM that can be made. A
yes.
For each TPM, there is a special choice of inner product that can be made so that the entire inner product or metric is the differentiable function.
Yeah.
And that works
I
for
mean, the
every
metric is,
manifold.
I mean, it's not a unique choice, but it's a special choice. Yes.
Special choice, and that makes it a hard problem, because I mean it's not a trivial problem, let's say. It's not a
Yeah.
trivial problem, and there is something to be done there. Okay.
Yeah. You
And
need to know some, like, a little bit more math than high school math.
yeah, of course, now it's clear to me that there is something special going on here. Okay,
Yeah.
okay,
That's why
sorry,
you
please
need
continue.
this kind of partition of unity kind of rigor.
Yeah,
So,
yeah,
so that you can patch them up. Well, so that's the thing, right? So, for example, okay, this is actually this leads to a great question. So, for let me okay, this is something that I have learned, this I want to share, that when you are on a manifold, it locally looks like Rn, right? So you differentiate a function, you essentially are differentiating in Rn. I mean, okay, differentiation doesn't have any meaning, but if you look at the continuity, for example, of a function, then continuity of a function on a manifold is just like Rn, because locally a manifold looks like Rn, and continuity is a local property at a point. At a point, continuity is local property. So now the question is, so okay, local properties like looking at continuity can be uh, done on charts. How do you do global calculations? For example, integration. Integration on the manifold is a global calculation. You take the entire manifold into account when you are integrating, for example, a differential form. So then you, whenever you try to do global stuff in terms of the local stuff, that you want to say, okay, I want to integrate something, but I want to essentially integrate on local charts. But
right,
after completing the integration, it should be an integration on the whole manifold. Then
right,
you use
right,
this technique called partition of unity, where you
yeah,
patch local things to global data. So
right, yeah, yeah, yeah. Great, something special is going on, I see. Okay,
right.
please continue.
So now the thing is, now let us talk about length of a curve. Now, for understanding length of a curve, first of all, you should first note that this Riemannian metric acts on tangent vectors and gives you an inner product of tangent vectors. That is very important. They are tangent vectors. Now, let's revisit something from high school physics or high school math. That suppose um, you are on a curve. Suppose the curve is on R2, that as I have drawn, it's a planar curve, and the curve is C of t, which means C is the curve from, for example, 0, 1 to our R2, and C of t is the at a point t, the coordinate is given by C of t. It's the parametrization of the curve. Now the question is, I think you all know from high school physics that suppose C of t is basically the equation of path of an ant. An ant in a very bad drawing is probably moving along this curve with the position vector as C of t with respect to the origin here. Then this is your C of t basically. Then the question is, what is the velocity at this point C of t for this ant on this curve? And the answer to that is, it is given by a tangent. What is that? That is C prime of t. So now you see here the tangent spaces come into picture. Tangent to the curve also is part of tangent to R2 because curve is in R2. So in that case, this C prime t will also be in the tangent space of R2. So in that case, this we are getting at whenever we actually talk about the velocity of a curve, this C prime t actually lives on the tangent space of the ambient manifold in which the curve is sitting. So then we all know how to calculate length, right? Because the length of a curve, if we talk about this R2 setting, so first length, what is length? What is length? Is length of the curve is basically, if the ant goes from A to B, then the length is basically the distance traversed by the ant from A to B. And how do you go there? How do you calculate this distance? Well, we know from high school that distance is basically integral of speed. What is speed? Speed is nothing but the length of the velocity vector or the norm of the velocity vector. So if you integrate that from 0 to 1, you get the length of the curve C. So exactly the same thing is going to be done here, because look at this length. What is this length? The length we know is square root of C prime t dot product with C prime t, right? This is the definition of length of a vector. It's the square root of the dot product of the vector with itself. Now, on a Riemannian manifold, because we have an inner product which is the metric, this dot product is our metric. So then, on a Riemannian manifold, M comma G, where G is our metric, M is our Riemannian manifold. In that case, suppose you have a curve from an interval AB in R to M. In that case, the length of the curve can be calculated by you integrate from A to B, just like before. You integrate from 0 to 1 of the speed. Here, the speed would be the Riemannian metric on, gamma prime t, gamma prime t, dt. So this is the length. Now, again, exactly same thing is going on. Just have a look. Here we had dot product. Instead of dot product, we are having the metric because that is also an inner product, just like dot product. Inner product basically means dot product, if you don't know what inner product is. So inner product is just a fancy name for dot product with the similar properties. So then inner product of these two are calculated, and then you take the square root so that you get the speed. This is the velocity, and this whole thing is the speed. And you integrate the speed, you get the distance, and the distance traversed is nothing but the length. So now this is called the length functional. Again, the word functional might be a bit confusing. It's just a function. It calculates the length. So then once you calculate the length of a curve, you can define the distance function on a Riemannian manifold. So suppose again this is our manifold M, you want to calculate the distance between 2 points P and Q. So how do you calculate? First of all, note that you cannot think of, you may say that, okay, locally a manifold looks like Rn, so I can just use the distance function of Rn. No, it cannot be done, because if P and Q are far apart from each other, then in this locality P might look, I mean around P it might look like Rn. In this locality around Q it might look like Rn, but how do you connect from this locality to this locality? There is no unique way of connecting. So in that case, this Riemannian metric will help you to calculate distance between 2 points. And how do you do that? dg pq, dg, because it depends on the Riemannian metric, is nothing but the infimum. If you don't know what infimum is, it is just minimum. Infimum of all the length of the curves such that gamma is a piecewise continuous. Just think of them as continuous from now. Differentiable, actually not continuous, continuously differentiable curve from P to Q. So basically, if you have a curve like this, which is like piecewise continuous, then you calculate the length of this curve using this formula. Obviously, you have to calculate this part and then this part and then this part and add them together. However, you take all such lengths of all the curves, then join from P to Q and take their minimum. You can prove this is a distance function. There are certain properties for the distance function to hold, and you will see that all these properties are held, and thus with this distance function, mdg becomes a metric space. Metric space means it is a space or a set where you can measure distance between 2 points. For example, in R2, you have the Euclidean metric where the distance between the point P and point Q, P has vector v1, v2, Q has vector u1, u2. The distance is v1 minus u1 square plus v2 minus u2 square, right? This is dpq in the Euclidean setting. So similarly, we have a distance function on a manifold coming from this metric. Now we talk about completeness of the metric. Again, you might think that I'm covering a lot of things without any context. Believe me, when we go to my research area, all these things will become relevant. I give you my guarantee about it. So completeness of the metric. So what do you mean by completeness? So there are two definitions of completeness, and they're actually equivalent. So let's try to talk about two types of completeness. One is geodesically complete. If any of you is a who wants to like read Stephen Hawking's books or things like that, which are like popular science, then you might you probably know this word called geodesic. Geodesic, some people know this word as straight lines on curved surfaces. Or if you try to draw a straight line on a curved surface, that becomes geodesic. Well, yeah, that's kind of true. And so basically, you have this length functional, right? If you have a curve gamma from A to B to the manifold M, then you have this length functional gamma prime t dt. A geodesic is an extremizer of this functional, which means it is either the minimizer or the maximizer. And then, I mean, it's the curve for which this length becomes maximum or minimum. Now the question is, like, do you know examples of geodesic? Well, yes. So suppose this is a sphere. Then look at these 2 points. Suppose these are 2 points on the equator. I mean, on first, okay, yeah, the 2 points on the equator. If these are the poles, then you can join these 2 points by this, where this line is drawn as is the part of the equatorial line. This will be a geodesic. Also, you can take the opposite of the line, like you go around the sphere and then join them. That is also equatorial, but just the, in some sense, the complement of this short line here. That is also a geodesic. And the fun thing is, this bigger line is the length maximizer, the smaller line is the length minimizer. But both basically extremize this quantity here. That's why it's both of them are geodesics. And if somebody knows a little bit of variational calculus, then this is a functional. To find the extremizer of this functional, you can write the Euler-Lagrange equation. And if you write that, you get an ODE or system of ODEs to solve on the manifold, from which you explicitly get an equation of the geodesic with respect to the metric, of course. It's the function of the metric. And that is called the geodesic equation. However, now we have introduced the concept of a geodesic. So what do you mean by geodesically complete? Geodesically complete means that, okay, yeah. For any, this concept means for any geodesic gamma t starting from a point P in M is defined for all t in real. Now, what do you mean by this? Well, to understand this, basically it means that suppose you are on a manifold, you have a point P, you start defining a geodesic and you can define it forever. Like this. Basically, yeah, so it is really like this. Now, you might think that this is a very difficult way of defining something. What do you mean by this? Well, there is an easier notion to understand completeness. For that, we recall something called Hoff-Renau theorem, which again I'm not going to prove. M is geodesically complete if and only if M dg is the distance function that we defined from the metric before. So M is geodesically complete if and only if this is a complete metric space. Now, what do you mean by complete metric space? Complete metric space is a metric space where every Cauchy sequence converges. Now, what do you mean by convergence of every Cauchy sequence converges? Cauchy sequence means that suppose you have a sequence of points, and as you go on in the sequence, the distance between the 2 points become arbitrarily less. You are on a metric space, so you can measure distance between points, and Cauchy sequence is just an array of points, an infinite array of points. As you go on in the array, you will see the distance between 2 consecutive points is becoming arbitrarily less. Now, such sequences may not converge in certain spaces depending on the space, but a complete metric space says that any sequence where the distance between points become arbitrarily small must converge to a point, which means for every, I mean, if this is the limiting point L, then for any neighborhood of the limiting point, there would be many points of the sequence in that neighborhood. Anyways, we don't have to go into the definition of convergence and stuff like that. The idea is you can think of the converging point as a limit. You know concept of limit, right? So basically it means that if you have a sequence of points where the distance between points is arbitrarily decreasing as you go on in the sequence, there is a limit of that sequence. So now we know now what complete uh, Riemannian manifold means. It means either geodesically complete or equivalently M comma DG is a complete metric space.
So, sorry, Kushomo, sorry to interrupt again. So, do you the picture that you drew here? It showed that if you go along a sphere, starting from any point, then you would be able to move for infinite amount of time, right?
I mean, it
Now,
depends on the metric, but yeah, for certain metrics, yes.
okay,
Like for example,
so
if you have the hyperbolic metric, then yes.
okay.
It depends on the
So,
metric. Otherwise, no.
okay. So it's defined for all t in R. Does it
Yeah,
mean
it
that?
means basically that it's not
So
only
what would happen
defined
on a
on a
sphere?
compact interval, but it's defined on the entire real line.
Yes. Sorry, can you say that one more time?
So normally when we define curves above, we just define on a compact interval in R.
Right,
But
right.
here, for a geodesically complete manifold, you can define the function gamma for all values of t, not only in a compact interval, but in an entire real line.
So what would be the case for a sphere?
For hyperbolic metric, you can draw it. It is hard to draw it actually,
Yeah,
because
of course.
it hyperbolic metric, the geometry is not easy to draw. So I don't know how to draw
But
it. But
the normal, if I take the spherical metric in the sense that the big circles are the geodesics, in that
yeah,
particular scenario, so is it geodesically complete?
I don't think so. I'm not sure. I have to look it
Okay,
up.
okay. Just
Yeah.
thinking about it. Okay,
Yeah,
all right. Thank
basically
you.
there is another way to understand geodesic completeness. That is, a manifold is geodesically complete if length of gamma tends to infinity as gamma tends to the boundary of M. But this is only applicable for manifolds with boundaries. So I don't want to get into this. But yeah, that's the idea. I mean, as you go on, as you go try to go to the boundary of the manifold, if your length of the curve becomes infinite, then it's called geodesically complete for any curve if it becomes infinite.
Okay, okay. Thank you.
So yeah, these are things that I don't work on at all. So I don't. Uh, uh, I did them like 3 years back, and now I forgot everything. But anyways, now the thing is, we are till now talking entirely about real manifolds. All our manifold locally look like Rn. We have defined differential forms. We have defined um, for example, um, Riemannian metric. What happens in complex manifolds? So let's go back to complex manifolds. So before we go back to complex, before we start from here, I would like to recall certain things that we covered a few weeks back. So if you remember, so Asunita, can you see my slides?
Yes, I can.
Great.
Perfect.
So now if you are in Cn, then we define these operators here. One is del zz bar and del zz. And there you see that these are nothing but the linear combination, some complex linear combinations of these real valued partial derivatives. Now, previously you saw that these real partial derivatives at a point make up the tangent space, the real tangent space. Similarly, these derivatives here will make up the complex tangent space, which are nothing but the linear combinations of the real vectors, complex linear combinations. And then, um, so now let's try to go to complex manifold theory, and M be a complex manifold of complex dimension n. You always have to be careful whenever you are working on a complex manifold, because complex manifold has complex dimension n. It means it has real dimension 2n. Why? Because C itself has real dimension 2. A complex plane is same as R2. However, now a Hermitian metric on M is given by a positive definite Hermitian inner product that goes, again, it's an inner product that goes from TZM to TZM bar to C. Basically, you can think of this as the space where all the del z's live, and here this is the space where all del z bars live. Now, again, it is given by a inner product, but it's a Hermitian inner product. You don't have to pay attention to the word Hermitian right now. Hermitian inner product simply means it is linear in first coordinate and conjugate linear in the second coordinate, which means if you multiply the second coordinate by a complex number, the conjugate of the complex number comes out. So now you can define, so this inner product, so in local coordinates, suppose you have a vector, uh, for example, let's put it this way. In local coordinates, this inner product is given by a positive definite Hermitian matrix. Okay, and it is given Hij, which is del Di del. Okay. Now again, these things might not be, you might not be comfortable with it if you are seeing it for the first time. Don't worry about it. Just think it's the inner product. So now, in other words, if you have this matrix, which is the positive definite Hermitian matrix. Hermitian matrix means a matrix is called Hermitian if its conjugate transpose is equal to itself. Then the metric is given by summation ij hij dzi dzj. What are these? This is just, we talked about it. We briefly talked about it. This is a differential form. This is a differential form. It takes the vector del zi del z bar and gives you 1. For all the other vectors, if you take some if you take del k del z l bar, it will become 0. It is basically a dual vector of this whole vector here. Anyways, the point is that this tensor product sign here means that this acts on this acts on this. They separately act on two components. So now we are going to come to a little bit involved topic. That is, we defined a metric, but previously we had something called differential 2 forms or 2n forms or nn forms. How do you define, I mean, is there a connection between a metric and differential forms? The answer is yes. So how do you get that? Well, suppose because it's a metric, it's positive definite, right? You can, I mean, take it for granted. Any positive definite metric can be written as something like this. These are basically orthonormal coframe for the Hermitian metric, which is nothing but it's a space of differential forms which are it's basically an orthonormal basis for the space of differential forms. Orthonormal basis, I think you all know, basically these means the basis vectors are unit length and the basis vectors, well, it doesn't have to be orthonormal, it's just orthogonal. So basically, which means that two independent basis vectors are perpendicular to each other with respect to the metric that we have defined, this here. And we can always have an orthogonal coframe by the Gram-Schmidt's process or something like that. And then if you ds, so ds square is this. Now these are complex differential forms, right? So you can write them as alpha I plus square root of -1 beta I. Just write them as real and imaginary parts. So these are all now real forms. Because we had a complex form, we wrote them in its real and imaginary parts, just like you do for complex variables. So then this ds square becomes alpha I plus square root 1 beta I tensor alpha I minus square root 1 beta I. This minus sign is coming because of the conjugation here. And now you tensor product is bilinear, and using that, if you expand everything, you get this plus square root of -1 alpha I beta I, sorry, alpha I beta I plus beta I alpha I. Okay, so this is the real part of ds square. This is the imaginary part of ds square. Both are all are differential forms. These are all differential forms in some sense. They are not exactly differential forms. Okay, this is a differential form. And I'm not going to give you the proof right now. Just accept it. This is actually not a differential form. It's a tensor product of differential real forms. So now ds square was our metric which calculates the inner product between two vectors. How? Again, we saw that before. You express a vector in terms of the basis vector del zi and del zz bar, and then you take the inner product. When you take the inner product, you will see that only certain terms are going to be there because of this relation here, and most of the other terms will vanish because of this relation here. Now, once you have this metric, then there is an associated 1 form omega to this metric, which is nothing but half of imaginary part of ds square, which is nothing but coming from here. Okay, and actually it's I by 2. So I mean, sorry, I is again confusing. It is square root of -1. So it is just defined like that. So when you have a metric, it is actually this real part of ds square would be a Riemannian metric. So when you have a Hermitian metric like this, the real part of the Hermitian metric is a Riemannian metric, and the imaginary part of the Hermitian metric is a differential 1-1 form. What do you mean by 1-1 form? It looks like dzi wedge dzj bar, something like this. This gives you the 1 here. This conjugate thing gives you a 1 here. That's it. We will talk more about these kind of forms. And this is a fact. So we saw that whenever you have a Hermitian metric, you have an associated 1-1 form. The converse is also true. If you have a positive 1-1 form also gives a Hermitian metric, and hence a Riemannian metric, because the real part of the Hermitian metric is a Riemannian metric. So anyways, these are all extremely convoluted probably at this point. Don't worry about this. We will come back to these things again when we need them. For example, let's just give one example here. Hermitian metric on Cn, because it's a complex manifold, is dA square, which is given as y from 1 to n dvi tensor dvi bar. This is nothing but the Euclidean metric, just as we saw before. This is the Euclidean metric on Cn. Anyways, the point is Euclidean metric on Cn, which is same as R of 2n. Euclidean metric is with respect to real variables. Now we will come to very, very important concepts corresponding to metrics, which is the concept of curvature. Okay. Before we talk about curvature, we need to talk about connections. Now, these is, as we are going, actually, the topic is becoming very, very involved. Connection, the idea of connection is not that difficult. So let's just motivate connections first. Connections on a Riemannian manifold is nothing but a way of differentiating. You cannot differentiate on Riemannian manifolds in a proper way, because differentiation, because Riemannian, suppose you have a manifold M, then I know differentiation is a local property, but you can have different charts around the point. You can express a chart in terms of U, then you can have another chart which is V. So what do you mean by differentiation? In those two charts, the coordinates are different. If the coordinates are different, then differential values would be very, very different. However, there is a way to think about it, and we will just vaguely define it. Before that, let's just try to motivate something. So what is the motivation? So suppose suppose we have a vector field y be a vector field on Rn. If y is a vector field on Rn, first of all, for functions that we know, for a function f on Rn, we can talk about, suppose we have a function f, this is your Rn, you have a function f, then you can talk about the directional derivative of the function along a direction v, which means if v is a vector at a point P where you have defined a function, I should not draw a function with a point, but suppose you have a function f on Rn, then if you have a point P and you have a direction from that point, you may want to know how much the function, at what rate is the function changing in that direction. So there, to understand that, you might want to know what is the rate of change. Okay, you might want to know the rate of change of function in that direction, which we often write as the directional derivative of the function at the point P along the direction V. But previously we defined something which actually directly denotes this thing, which is V of f, because we expressed our vectors as partial derivatives. So when these partial derivatives act on the function f, and then you evaluate that at the point P, you basically get the directional derivative of the function at at the direction v at the point P. So when you have a function, you know how to calculate the directional derivative of the function. By the way, by function, I mean it's a scalar function. It takes from Rn to R. However, what happens when you have a vector valued function or a vector field, for example? Suppose y is a vector field on Rn, which means y gives you a function. Y it takes an input as a input as a point of Rn and gives you a vector in output. So how do you calculate that? Well, it is not that difficult. So y will have several components. Suppose y1 up to yn. Suppose y is a vector field of Rn. Y goes from Rn to Rn. So you feed it a point P and it gives you y1p up to ynp. Then y has these components y1 up to Rn, yn. This is just multivariable calculus. You basically have a function which has multiple components. And then if v is a vector at a point P in Rn, then we may try to define, we denote it like this. This is the, and evaluate this at P. This is the directional derivative of y at P in direction of V. So now we can define directional derivatives along of a vector field, not a function, not a scalar valued function. Well, for that, suppose V is given by, okay. How do you give this directional derivative? The directional derivative would be a vector. Because it is differentiating a vector field, the answer would be a vector. And how will you give it? Well, the vector field V acts on each of these components. Well, if y is a vector field, which means it takes a point and gives the vector as output, then each of these components are nothing but a scalar function. They take a point and give you a function, gives you a scalar as output. So it is nothing but vy1 del x1 at the point P plus v plus vy2 del x2 at the point P plus dot 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 vyn del xn at the point P. Which means what? V of y1 gives you a function because V is a vector field, it's a differentiation. Vector field is a differentiation. V of y1 gives you a function by differentiating the function y1. Then you evaluate that at P and then write it in terms of the base along with the basis vector del x1. You can just think of this as E1, which is 1 0 0 0 0. So now you know now how to differentiate a vector field with respect to a vector. Then the question is, if X is another vector field, then you can define the differentiation of a vector field with respect to another vector field. Previously, this V was a vector at a point. Now this X is a vector field defined throughout Rn. And there it is again the same definition. But now you see the only difference is we are not evaluating any of these things at any of these points. Because it is a vector field now. This is a function now. Previously, we had a function v of y1, but then we were evaluating that at a point. So this was becoming a number. But now this is a function. So this is a vector field. So vector, you can define the directional derivative of a vector field with respect to another vector field, and you get a vector field as answer. So for next time, because we are ending today, we will start to define affine connection. And after we define affine connection, we talk about the covariant derivative and parallel transport, and then probably towards the concept of Ricci curvature, which is very important. After that, we will go back to our slides and we will directly jump on to my research area.
Thank you, Shomo. It was wonderful. I think the main issue is, and this is, um, I mean, I want to communicate these to all of you who are here as listeners, that the case with most research level talks, even with many courses, are that you would probably understand only 20% of it when you first hear it. And that's if you are lucky. I mean, I if you have seen the topic before and so on. And this is the story about any research level activity. And most of you have not seen differential geometry before, so that's a challenge. But I think Shomo is doing a fantastic job in going down to that level and trying to bring the things to life. So thanks to him for that. I will post this video, the recording of this video, in YouTube again, as the previous ones are also posted. This one will also be posted. So I would strongly recommend that you go through the previous recordings and this one. And if you have a question, have some questions, you can definitely post it in the WhatsApp groups that you're added to. And I'm and we will see you next time again. Thank you, Shoma, again for your
Yeah,
time. Okay.
I think we will need two lectures,
Yeah,
but the
yeah,
thing is, but the good thing is that I mean, even if the concepts are very difficult sometimes, there is, you can always. I am trying to like, that's why I'm trying to like motivate the concept of directional
yeah,
derivative of vector fields from Rn, so that
yeah,
later you can just think of manifolds locally as Rn, and then you can do all this. But
yeah,
again, yes, little bit of knowledge is required, but let's see. I mean, at some point you have to make a leap of faith if you are doing,
yeah,
if you are
yeah.
hearing a research
Yeah,
talk.
in fact, I will tell you this, Shomo, that eh, from the next one, you can just assume that all that you have taught has been well understood, which will not be the case. But you can just assume that they're well understood and continue the discussion, because what we want is some of these kids suffering through the pain of not understanding, take a leap of faith and start digging the things from the hole, right? We want that to happen.
I can tell one thing in addition to what Ashonida is saying, that is even when we are doing research, we do that. We don't
Yep.
really understand all the things when we are doing research, but we sometimes just take leaps of faith. We just assume something is true and then we start working on it.
Absolutely, absolutely. We do it all the time.
Yeah,
Anyway, so thank you everyone for joining in. We will see you next week. Thank you, Shomo, again. Take care. Good night
absolutely.
and good day to you.
You
Bye.
too. You too.